Welcome all to this new session which is going to start Chapter 17, Planar Kinetics of a Rigid Body, Force and Acceleration. In particular, we are going to discuss mass moment of inertia. The objectives of this session is, as I said, to discuss the moment of inertia of a body. We will also discuss parallel axis theorem, radius of gyration, moment of inertia for a composite body. When a non-zero moment is applied on a rigid body, this body would experience angular acceleration. The relation between the applied moment and the angular acceleration alpha is analogous to the relation between the force and acceleration. So the Newton's second law, F is equal to ma, so F as a force vector equals to the mass scalar multiplied by the acceleration as a vector. And on the other hand, if the body was under an applied moment, we can write that the moment is equal to I alpha. And if you see here, we have a force, here we have a moment, here we have a mass, and here we have the moment of inertia, here we have the acceleration, and here we have the angular acceleration. So as we said, the mass analog is called the moment of inertia, I, of an object. So if we have this rigid body, and we take an infinitesimal mass dm over a distance r, then the moment of inertia is defined as I, which is equal to the integral over the mass r square dm, where r is the moment arm, and you should know that the unit of the moment of inertia is kilogram meter square or slug feet square. We know that mass equals to the density by volume, so we can use this as this is the mass element, dm equals to the density rho multiplied by the volume element, and for that we can rewrite or express the moment of inertia I using volume and density, and in here we have to integrate over the volume r square rho dv. Depending on the geometry of the rigid body, there are standard volume elements like the shell element and the disk element as shown here in those two diagrams. So for the shell element, we will have the volume dv is equal to 2 by y multiplied by z dy, and for the disk we have dv is equal to by y square dy. Now let's have an example on how to use the shell or the disk element to determine the moment of inertia for a body. Here we have a cylinder as shown, and this cylinder has a constant density, and we would like to determine its moment of inertia along the z-axis. The cylinder has a radius of capital R and a height of h. Now clearly the most suitable element here is the shell element, which is represented down there. So this is the shell element. It has a radius r and a differential thickness dr, and the height we will keep it h. And if we want to write down this volume shell element, it's going to be dv is equal to 2 by r multiplied by h and then by dr. Now we know that the volume element, the mass element dm is equal to rho dv. So if we substitute, we will get rho 2 by hr dr. Now we can express the moment of inertia for that element. So because it's for the element, we get diz, which is equal to r squared dm. This is the definition of the moment of inertia. Now we substitute and we get 2 rho by h r cube dr. Now if we want to get the moment of inertia, we have to integrate over the entire body. So Iz is equal to the integral over the mass of r squared dm, which is equal to 2 rho by the integration from 0 all the way to capital r cube dr. And from here, from this one, we get rho by over 2 r to the power 4 h. The mass, the entire mass of the cylinder, m, is equal to the integral over the mass for the mass element, and we know what is dm. It is 2 rho by h, the integration from 0 to capital R dr. And if we integrate this, we will get rho by h r squared. Now from the previous slide, we showed that Iz is equal to rho pi over 2 r to the power 4 h. Now I will rewrite this as rho by h r squared multiplied by half r squared. Now clearly this term is the mass. So I can now say that Iz for a cylinder is equal to 1 over 2 mr squared. Now here we have moments of inertia for some common geometric solid. And if you see, this is the cylinder, and we have Izz half mr squared as we derived previously. And if you look here, because of the symmetry, the moment of inertia along the y and x axis is the same, and it is equals to half 1 over 12 m 3r squared plus h squared. This is again the moment of inertia for different axes for a thin plate. And here we have the moment of inertia along different axes for a cylinder rod as well as thin circular disc. Finally, this is the moment of inertia for a thin ring, and we have it here for again Ixx, Iyy, and Izz. Now we might encounter situations where we need to calculate the moment of inertia about an axis which is not the axis that passes through the mass center, G. And for that we need to use the well-known famous parallel axis theorem. So I am sure you are familiar with this, but just to remind you, if we want to calculate the moment of inertia about an axis O, then it is equal to the moment of inertia about the mass center, Ig, plus the mass multiplied by d squared, where Ig, as we said, is the moment of inertia for mass center, g, m is the mass of the body, d is the perpendicular distance between the parallel axes, which is the axis of the center of gravity and the axis at point O. Many standards and handbooks tabulate the moment of inertia in terms of radius of gyration, which is related to the mass and moment of inertia as follows. I is equal to mk squared, where k is the radius of gyration. Or we can say that k, the radius of gyration, is equal to I over m. Now, if we have a composite body like this, we cannot determine the center of gravity by inspection. We rather need to do some calculation. So in this example, we have this pendulum, which has part OA and BC. Each one of those has a weight of 10 pounds. So this is 10 pounds, and this one is 10 pounds. And I'm going to mark them with different colors. So this is the first part, and this one in blue is the second part. This is why we call it composite body. Now, to calculate the center of mass, we need to set a reference. So I'm going to set the reference at point O. So this is our reference. And if measured from this reference, we have y bar, which is unknown, and it represents the location of the center of gravity. Now, also, we would need to determine the center of mass for each part with respect to the reference. So, since the length of part OA is 2 feet, then at 1 feet from the reference, we will have its mass center. And for that, I'm just gonna mark it here, and again in blue. So at the center here, we have 1 feet. Now we are going to call this one y tilde. So this is y tilde for OA. Now for the other part, which is PO, y tilde is basically 2, which is 2 feet right here. This is its center of mass from the reference. Now, the equation says that the center of mass for the composite body is equal to the sum of the y tilde multiplied by m divided by the sum of all masses. Now, if we want to apply this, then the center of mass is equal to 1 multiplied by 10 divided by 32.2 plus 2 multiplied by 10 divided by 32.2 divided by 10 over 32.2 plus 10 divided by 32.2. So let me explain what are those terms. The first one here is this. This one is y tilde OA. And this one is the mass of OA. Since we have been given the weight as 10 pounds, we have to divide it by the gravitational acceleration, which is in feet per second, 32.2. Now, then we have the y tilde for BC, and this is the mass for BC. And then we just added the mass. So this is the masses BC, and this one is the mass of OA. Now, if we calculate this, we will get y bar as 1.5 feet. And this is the center of gravity for the composite body. Here we have a procedure for determining the moment of inertia for a composite body. So if we have a composite body, we need to first divide it into simple bodies, and then we need to compute the moment of inertia for each simple body about its centroidal axis. Then we need to transfer those centroidal moments into the required axis using the parallel axis theorem. Now, once you do that, you can sum the moment of inertia for each simple body about the parallel reference axis, and which is basically the moment of inertia for the entire body. Now, any cutout, a hole or any sort of cutout, must be assigned a negative moment. So it should be subtracted, and all other areas considered to be positive. Now, because we know the moment of inertia for the cylinder, which is I equals to 1 over 2 mr square, where r is the radius of the cylinder, then we can determine the moment of inertia for a hollow cylinder. Now, let's assume that we have this hollow cylinder with a capital mass m and an outer radius r1 and an inner radius r2. So what are we going to do? We will compose this into one big cylinder and one small, and we will subtract them. So the moment of inertia will come out to be I is equal to 1 over 2 m1 r1 square minus 1 over 2 m2 r2 square, which is basically equal to 1 over 2 capital M r1 square minus r2 square. Now let's have an example. So the pendulum is suspended from the pin at O, so that's point O, and consists of two thin rods, OA and BC, each having a weight of 10 pounds. Determine the moment of inertia of the pendulum about an axis passing through point O, the mass center G of the pendulum. Now, to solve this, we would need to determine the moment of inertia for each rod about point O. Now, the equation for a moment of inertia of a rod rotating about point O, which is the end of the rod, not its center of gravity, is this. I OA about O is equal to 1 over 3 ml square. So if I substitute, I will have 1 over 3 and then 10 pounds divided by 32.2 feet per second squared, and then I have to multiply this by the length, which is 2 feet square, and I will get the moment of inertia as 0.414 slug feet square. Now, for the other rod, which is BC, we would need to calculate its moment of inertia about point O, not about its center of gravity. For that, we would need the parallel axis theorem, which says that first, calculate the moment of inertia for this rod about its center of gravity, and then use the parallel axis theorem, md square, to transfer it to O. So this is going to be I BC about O is equal to 1 over 12 ml square. So this part is the moment of inertia for a rod around its center of gravity, right here in the middle. But since I want it at O, I have to use the parallel axis theorem, which says that you have to add md square term. So if I substitute, I will have 1 over 12, and then again 10 pound divided by 32.2 feet per second square, and then I have to multiply by the length. The length of this one, 1 feet and 1 feet, is still 2, similar to the length of this one, and I will have 2 feet square plus the mass, which is 10 over 32.2 multiplied by d. Now d square is the distance from the center of gravity for the body to the center of the rotation, which is O, which is clearly 2 feet. So I will have to add 2 squared. Now I will get 1.346 slug feet squared. Now IO, which is the moment of inertia for the entire body about point O, is basically the addition. So the sum of 0.414 plus 1.346, and this is going to give you 1.76 slug feet squared. On the next part, we would like to determine the moment of inertia for this composite body, but around its center of gravity. Now, if you recall from the previous slide, we determined y bar as 1.5 feet. And since we know that IO is equal to IG plus MD squared, then 1.76 is equal to IG plus, now here the difference is the mass. The mass is the mass of the two parts, OA and BC. So we have 10 and 10, so 20 pounds divided by 32.2. And then we have to have d square as 1.5, because what are we doing here is that the body is rotating about point O, but we would like to determine its moment of inertia about point G, which is 1.5 at distance from the center of the rotation. And we'll have this one as 1.5 squared. And for that, I will get IG equals to 0.362 slug feet squared. To summarize, we have discussed the moment of inertia of a body, the parallel axis theorem, the radius of gyration. We also talked about the moment of inertia for a composite body and how to determine the mass center. That's it. Thank you.